Swayam Prabha. Digital India. Educated India.
Welcome to the subject Advanced Digital Image Processing and Computer Vision. We are discussing about projective transformation under the projective geometry. In the last lecture, we discussed how we can estimate the projective transformation given the point correspondences. Let us discuss today that different kinds of projective transformations and different specialties, cases of this projective transformation. First, let us consider this case when the projective transformation is induced by a plane, and as you can see that I have just considered a plane here, and in the implicit 3D space which is defining the projections, and you have the projection plane, 2D projection plane. So, consider a point x in that plane, and if I take the respective projection of x, so if I draw the projection ray from x to the center of projection O, so in fact you can consider also say two multi-view considerations, that there are another frame of projection where we have another projective space, and because it's transformations we are considering, so we are taking two-dimensional projective space, and then we will see that the respective mapping of the points and one-to-one correspondences of points of the same scene point which are projected there, that defines a projective transformation. That is what is the transformation induced by a plane. So, in this case, let us consider say this being the projected point. So, there is a point say which is x, small x I have denoted, and say the other projective space you have a point x prime. Now, as I mentioned that the mapping between this and this, so we consider so this is uniquely defined for x prime is uniquely defined from x prime, x is uniquely defined with these configurations. If I take for example any other point say y, so once again I can draw this projection ray, I can form the projection, I can compute the projection from this, get the projection, and similarly if I consider a projection ray formed from y to the center of projections, and let us consider this is the corresponding projection mapping. So, all this mapping they are related with a projective transformation as we mentioned, which means that when I am expressing these points x and x prime, so irrespective of this plane, so we don't bother about this plane, we are just simply observing these two set of points, because these are the projective spaces. For example, this is a camera where we are observing the image of the camera, and as you understand that this image itself can be considered a projective space underlying this imaging considerations, imaging system. Similarly, this is also another image of the same scene by another camera viewing, another camera locations or another imaging system, and now we are establishing the point correspondences. So, this is a projective element of a projective space, which we can write it as a column vector, 3 cross 1 column vector, and H is a 3 cross 3 matrix. So, if I can express x prime equal to hx, similarly I can express y prime equal to hy, and if I consider any line in that space, so similarly this also gets all these points in that line, they have certain scene points on this planar plane. So, this line also have certain kind of if I consider a line here in this scene, say this line is the projection of this line in the scene. So, similarly this will also have an image here, have a projection here, say this is the projection. So this line and this line, they get also mapped, and there we know that relationship, that if I say this line is L and say this line is L prime, in again the representation, line representation, the line projective space with those parameter set, coefficient set, what we use for representing a line in the form of algebraic equation in a two-dimensional coordinate space. So we can also write L prime is H of transpose of H inverse, which I am writing in this form, into L. Okay. So this is the relationships in a plane in a projective space. It's a general relationships, but from the point of view of plane induced transformation also, we can have some physical interpretation. So just summarize once again, these are the transformations between line, and these are the point and line transformation. This transformation is in general true for any projective transformation. Now we would like to also study another interesting fact, that when we are considering simply the mapping of two projective spaces and with the projective transformation. So as we understand that, say suppose there are two lines which are parallel in the sense of Euclidean. Say it's an image plane, and which could be also interpreted like a two-dimensional real space. So there you can have two parallel lines which are intersecting at infinity in the Euclidean sense. But again, these are also element of the projective space. So which means this point, two parallel lines are intersecting at some ideal points. So that is a consideration. Ideal points are the point at infinity along this direction. Now when we are taking the respective projections or respective mapping using this projective transformation in the transformed space, so this is a transformed projective space. So you will have so consider, say these are the two lines which are mapped to this. Say for example, I may say this is mapped to this, and say this is mapped to this, and applying this transformation, transpose of H inverse. So if it is L, so it is L prime. Say this is let me say this is something L tilde, and say this is L tilde prime, right? Now as you can see that they are actually intersecting. They are intersecting. They are not parallel in the sense of Euclidean. So they are intersecting in this due to transformation, because what happens that the ideal point, which is also lying at the at infinity, and as you know, ideal point should be some point in this ideal plane of this projective space. Now this point also has a finite representation. So I can apply a transformation on these points, and in fact that is what is mapped here. So it is the same, because this point is also lying on both the lines, and so this point transformed point also should lie on both the lines. So it's an intersecting point. So when it is intersecting, this point is called vanishing point, because you understand that if I move along this direction, you are also moving along these directions towards the point at infinity. They are intersections. So when you are moving along these directions, now naturally this is the point where actually you are, because it is moving towards the infinite point at infinity for the intersection. So it will move towards this intersecting point, but it will not cross beyond this point. That's why it is called vanishing point. It is as if as you move towards infinity, it will also move towards this point, and it will be converging. It's a limiting point, but you will not, since the point at infinity also you are not able to physically arrive. In this case, here also you are not going to physically arrive through this mapping. It would be just converging to that limiting, as a converging at the limiting point. So this point is called vanishing point of the projective transformation. So let me also show this thing with a little more clarity in this picture. Let's say this is the point of intersection, and as I mentioned that the ideal point which is the point of intersection of these two lines, these two parallel lines in the sense of Euclidean. So this will lie in some, so this is some ideal point. So finally this point should be mapped, and it can be expressed, as you can see, that this is basically in the column vector form. I can write it as b minus a0. It's a column vector. If I multiply it, that would give me the respective vanishing point of the parallel lines along the same directions. And the directions is given by this a and b. These are directions of the parallel line. So actually direction is b minus a, direction of the parallel lines. Now another fact is that, as we have seen earlier also, see all these ideal point, they are lying on the in the corresponding line projective space. These ideal points are lying at a particular line which is represented by 0, 0, 1. So in the line projective space, it is the scale dimension, if I can say, and this line is called line at infinity. So since these are so if I consider say another parallel line in these directions, so this will also give me some point of intersection, and this point of intersection and this point of intersection, whatever parallel line you can consider, all of them should be collinear, because the ideal points, they are all collinear. They are all lying on this line at infinity, and this line is called vanishing line. And as you understand that this line, then in that case it should be the transformation of the line at infinity. So line at infinity is represented in this form. So we can say that this is a vanishing line. Say this is a vanishing line. Say suppose this is a vanishing line. So we can get this is a vanishing line. So once again, so as I mentioned that if I just transform the line at infinity with this projective transformation and corresponding relationships related to the projective transformation H, then you get the vanishing line. And its interpretation is that all the parallel lines in this source projective space, they will be meeting at a point in the vanishing line in the transform space. That is the interpretation of vanishing point and vanishing line. So finally, to summarize all these transformations in a projective transformation, point and line transformation, we can see that point transformation can be expressed directly from the definition, that is x prime equals h into x. H is a 3 cross 3 non-singular matrix, and you understand x and x prime, they are all the elements of the projective 2D projective space, which is mean they are represented in a 3 vector form in the homogeneous coordinate system. Then the line transformations are given by L prime equals H minus T, H minus transpose L, which means transpose of H inverse L into L. And then vanishing point is the transformation of the point of intersection of the parallel lines in the original space, which is an ideal point. So if the line is given by in the direction ratio of A is to B, that is the direction ratio of a line, the vanishing point would be B minus A0. That is the ideal point. You know that's if I scale them also, if I multiply K also, that is also fine. But you will get the scaled representation. That means the scale ambiguity would be always there in this representation. So if I multiply H with this, then I will get the vanishing line, vanishing point. And vanishing line is the mapping of the ideal transformation of the line at infinity in the transform space, which means I will get this is a line at infinity which is given by 0, 0, 1. These are the column vector representation. That's why I have used transpose to write it in a concise form as in a row. So these are certain summaries regarding transformation of points and lines. Let us consider quickly an example by which we can give this, we can understand this computation. You consider a homography or projective transformation matrix. So this is a projective transformation matrix. You can see this is a 3 cross 3 matrix, and you can also find out that this matrix is non-singular. If it is singular, it could not be a projective transformation matrix. Now the problem is that you have to compute the transformation of line formed by 2 points. These are the 2 points, and they are all in projective space, which means in the actual observed image coordinates, it should be, as you know, that you have to divide it by 2. So these are equivalent in the R square space. This is 1, 2. Similarly, this one should be 2, 3. That is in the as an element of the real space. So there are different ways you can compute this method. What you can do, you can transform the points, and then in the transformation space, and as you know, 2 points define the line. So those 2 points, they are lying on the transformed line. So from there you can get the line by taking cross product of those 2 points. So in this case, we are transforming these 2 points, as I was telling you, 2, 4, 2 and 6, 9, 3 in the projective representation. So I just say it's the equivalent representation just to make these numbers bit more smaller, though they are not very large, but still some further reduction is possible. So I am taking the further reduction. As I mentioned, these are the canonical representation what we do, and then you take this cross product of these two. Earlier also we have computed this. So now I will simply show you the result. So if I perform, first you have to perform the transformation. So if I take the cross product, I will get the line in the original space. But in the transformed space, first you have to perform the transformation. So this is the transformation. That means if I multiply this matrix with this column vector, then I will get 5 minus 1, 11. Now this is a transformed point. So you note that 11 is a scale factor. So actual point in the transformed space would be 5 by 11 minus 1 by 11. And then this is the second point. So this point is transformed again 12, 3, 16. Once again, as I mentioned, actual point is 12 by 16 and 3 by 16 in the real space. Now what you need to do, you need to take the cross product of these two vectors to compute the line formed by these 2 points. So if I take the cross product, I will find these are the values of the cross product. So you can check, you can perform the cross product of these two vectors, and these are the components of the vectors. So which means that from here I get an equation of line as say minus 49x plus 52y plus 27 equals 0. So this is the line in the transformed space. What about the method 2? Method 2 is the other way. What you can do that first you compute the line, as I was telling you earlier also. Just take the 2 points in the source projective space, and then from the 2 points you compute the line, you define the line, and from that line you transform. So using the transformation transpose of H inverse. So this is what we are going to do. First you are computing the lines. I am showing in a bit, I should say, this is my convention. These are the vectors. And if I take the cross product, I get, this is the line, which means it is minus x plus y minus c equal to 0. Then, or minus 1 equal to 0. Then this is transformed line. So from there, transformed line would be this. I can compute that. So first thing here, you have to compute the inverse of H. That is a little more computationally, I should say, heavy. Earlier you did not compute inverse, and you should know how to compute the inverse. And in this case, since it is 3 cross 3 matrix, it is manageable. So this is the inverse of the matrix. So please go through the standard matrix algebra and find out how to compute the inverse. And then if I multiply this inverse matrix, so you have to transpose. Then you have to make a transpose and then multiply with L, and there you will get, now this is the equation. So you can see that you are getting same coefficients with a scale. So which means it is equivalent. Again, I can ignore the scale also and can express it as minus 49x plus 52y plus 27 equal to 0. Now let us consider the other example. Consider the vanishing line. We have to compute the vanishing line in the transformed space given a projective transformation. As you understand, each projective transformation will be associated with some vanishing line, because what it will transform? It will transform the line at infinity, which is given, that is 0, 0, 1. So just you multiply with the transpose of the inverse with 0, 0, 1, then you will get the vanishing line. So you get this, and if I perform this operation once again, then you will find that vanishing line is given by this expression. So this equation is 5x minus 15y plus 5 equal to 0. So vanishing line, I can write 5x minus 15y plus 5 equals 0. So these are few examples just to tell you about the properties of projective transformation, some computational methods and relationships between different entities. Now let us consider the different kinds of projective transformation. So we will find there are some special cases, and the first thing is that a projective transformation, it itself forms a linear group. So first, it is linear because this operation is linear. See, projective transformation operation is linear, and when it is a group, from the group algebra, we can show that first thing, that operation should be associative. There should be an identity element, and there should be an inverse. Now, since it's a matrix operation, and all 3 cross 3 matrix, and they are non-singular, they are invertible. Now, all these 3 properties are satisfied. So, just to give you an intuitive idea of associationships, so consider a projective space, and say these are the set of points which, after transformation, projective transformation, it becomes like this configurations. So corresponding points, there are 4 corners, they are transformed into correspondingly these 4 corners, and you can see that some sort of conversion of trapezium to parallelogram has happened. Now it is just an example. Similarly, from here, another transformation, suppose you derive this. Now this, which means that if I get any point, say this is a point x, say this is a point x prime, and say this is a point x double prime. So I can compute x prime by h1x, and then x double prime by h2 x prime. So which means, again, I can write h2 and x prime again write h1x, which means if I consider the multiplication of h2 and h1, and that transformation, that itself will be given directly, I can get this mapping by a transformation which is equivalent to h2 h1. So it is a cascade of transformation. So h equal to h2 h1. So this is the associationship. So you can just make this cascade, and since matrix multiplication is association, so you can, in any order, you can compute those simplify those expressions. Suppose there are 3 such transformations. So if I write like this, say h3 h2 h1, so these computations can be done in any particular order. So I can compute it like this, or I can compute it like this. So it depends. So this is the association operation. And as you understand that identity matrix is the respective identity element, because if I consider any particular identity matrix in the cascade, it will give me the same operation, same element I will get. That is the identity matrix, and also its inverse exists. That is why it forms a linear group. So as I mentioned, a cascade of transformation can be replaced by a single transform. This is explaining that association feature, as I was telling you, that if I consider 3 cascaded transformations, you can compute in different orders. Now the fact is that this projective transformation, there are several special cases. That means there are subgroups in these transformations. So it is a linear group and general projective transformation, and there is a subgroup which is called affine group, which is also a projective transformation, and whose characteristics, which is characterized by this form, that its last row is given by 0, 0, 1. So You can see that no, I can multiply with any scale and I can make it 00k. But when I specify it as 001, then suppose this row is made 001, then you understand with respect to these specifications, all these things have an unique representation. So with respect to this row, this transformation matrix is unique, but I can multiply with any scale, and that is how they are also equivalent projective transformation. Now, if it happens this row is in this form, then this transformation is also called affine projective transformation, and they form a group, which means if I cascade all the affine transformations, that means whose all Rust rows are 001 or 00k, whatever in the form, then the respective resulting operation would be also an affine operation. That is a formation of a group. And the inverse, as you can see, identity matrix itself is an affine transformation, and the inverse of affine transformation will be also an affine transformation. That's why it's an affine group. Then there is a special case further, there is a special case of affine group, which this is called Euclidean group. So what happens in this case, this upper left 2 cross 2 submatrix. Now this is orthogonal. So this is a characteristic. So this has to be 001, like it is also an affine transformation, 001 or 00k, whatever. And these 4 elements, they make an orthogonal matrix, which means if I take the dot product of these 2 rows, if I take the dot product of these 2 vectors, then that would be equal to 0. That is the meaning of that, they should be orthogonal. And of course, self dot product should be, a positive number, as you understand. Now, another special case, so this group is called Euclidean group. Further, another special case of Euclidean group is called oriented Euclidean group, where these are actually orthonormal. Actually, their determinant is equal to 1. So this is not only orthogonal, they are also orthonormal, right? So which means that if I also take the respective magnitudes of the vectors, that should be equal to 1, and the determinant is 1. So these are the factors. I mean, these are equivalent, of course. So you note that there is a hierarchy, because if the affine group is a special case of projective group, so affine group is also a projective linear group. Similarly, Euclidean group, it is an affine group, again, which means it is also a projective linear group. And oriented Euclidean group, it is also Euclidean group, which means this is also affine group. So transitively, this property is satisfied. So this is a kind of hierarchy we can see in the group itself. So you can find out that all identity matrix satisfy every, that means identity matrix is given in this form 1 0 0 0 1 0 0 0 1. So you can see that this is also affine. This is because last row is 0 0 1. You can see this 2 cross 2, this is also orthogonal, and this is also the orthonormal, and it has the determinant is equal to 1, that which means that. So since identity matrix itself is like this, so identity matrix is an element of all the group, and it has to be there because otherwise they cannot form a group. And the other fact is that if I take the inverse, it will be also an element of the same group. So this is rather it has certain interesting insight in this group structure. So these are the special cases. So let us try to understand each of these groups and see that what are the specialties of different groups, because whatever properties which are satisfied for in general for a projective group, those properties are also true for all its subgroups, and it goes down the hierarchy in the same fashion. So first we consider a general structure of a projective group. As you can see that in the projective group is the most general form, and we have represented in the form of a submatrix component. So let us understand this submatrix representation. You can see that HP is a 3 cross 3. This is a 3 cross 3 matrix. So when I am writing in the submatrix form, I am submatrix representation. So I am basically partitioning this matrix. Those elements are partitioned into certain submatrix structure. So this A is a 2 cross 2 structure. This T is a 2 cross 1 structure. So you can see that both A and T, they define the first two rows. And this B transpose, so in my notation, otherwise I always mention it as a column vector. Transpose means it has become row vector. So this B transpose is 1 cross 2. So you can see that even these two, they define the submatrix of two columns. And this V is a last element, it is just a scalar value 1 cross 1. So with this structure, with this kind of components, which means that I can make this partition in this way. So this corresponds to A, this corresponds to T, this corresponds to V transpose, and this corresponds to P. So this is the kind of submatrix, partitioning, and this representation. This representation makes the algebraic manipulation simpler, because the matrix algebra, which means this, for example, the multiplication, particularly multiplication operations. Now, the same rule of multiplication is extended in the submatrix form if dimensions are matched. So that so you can express larger matrix multiplications into the concise, analytical form using this kind of submatrix structure. That is the advantage you have, and also to find out different properties of those submatrix part. For that also, this kind of structure is useful. So you note that here V is given V1 and V2, and if V1, V2 is 0, 0, then it becomes an affine group. So, but no, for a general projective group, we are not assuming it could be also non-zero. So, we will assume that in general, they could be non-zero elements. Now, in this kind of structure, in the projective group, the general projective transformations property, what we discussed earlier, those are valid. Like it has 8 degrees of freedom, because there is a scale ambiguity. So, in a projective transformation matrix, there are 9 elements. So, you have this 9 elements, and since there is a scale ambiguity, so you can express all these elements in proportion to, say, sum of these elements. Say, let us consider H3. So that's why the degree of freedom should be 8. So it means 8 independent parameters are there. And how those 8 independent parameters are accounted for? So we can consider that there are different kinds of transformations by which this projective transformation may take place. So one is, you consider the scale transformation, which means scaling along 2 axes. So if you have a coordinate axis, and suppose you have a rectangle, now by scaling, I am basically enlarging. Scaling, it could be enlarging or shrinking, or I am shrinking. Say the aspect ratios, they get changed. If it is non-uniform scaling, then aspect ratio gets changed. So to scale means we have degrees of freedom. So if it is non-uniform, if it is uniform scaling, only one scale. That means it get enlarged or shrink, maintaining the same aspect ratio. Then you can perform 2 rotation. So you can perform rotation also. That means the axis, this axis, there are first you can perform translation. You can perform translation. So in the translation, you are translating this object. You know that one projective space, you can perform this translation. And rotation, actually you can perform rotation of axis, and also you can perform this non-uniform scaling. I have just shown along these rectilinear directions, but it could be any other direction. So with respect to that directions, you can define 2 orthogonal directions and apply those scaling. So there is a rotation for the coordinate transformation. Also there is a rotation involved for defining the scaling of its coordinates along any arbitrary direction. So these 2 rotation defines that, and 2 rotation means 2 parameters for rotations, 2 types of rotation. Translation is single because you are just moving x and y coordinates. So, and then line at infinity, as you understand, every transformation is associated with line at infinity. And when I am considering a line at infinity, actually line at infinities are associated with a direction. So you can see that it's a mapping of b minus a0, that is the vanishing point. So there are two parameters involved with respect to any line at infinity. And exactly, so two line at infinity. So these two are determining actually those two parameters. These are overall, these are determining these two parameters. So these two are for the line at infinity. So overall, you can see there are 8 degrees of freedom, and this is how this kind of parameters they are explaining these degrees of freedom. Otherwise, just from these coefficients, you may not be able to explain this part. With respect to transformation, you have to consider. So you consider a transformation of the ideal point, and you can see that the ideal point is not remaining ideal, which means that two parallel lines in the original space, again parallel in the sense of Euclidean sense, they become intersecting because they become finite. Because of this scale is not equal to, this may not be equal to 0, this may be equal to 0, this may not be equal to 0, depending upon the values. As you can see, V1 and V2, it determines that point of intersection. So line at infinity becomes finite, allows to observe vanishing points and horizon. So what are the things which are invariant with respect to projective transformations? First thing is that, as from the definition itself, as straight lines are mapped to a straight line, you know that collinearity is preserved. Since collinearity is preserved, concurrency of all straight lines, so straight lines which are intersecting at the same points, they should also intersect at the same point. Then the order of contacts in the straight line, that is also preserved. And another additional interesting feature which can be proved mathematically, that is called cross ratio or ratios of ratio, which is preserved. Now, just to explain what is it, I am not providing you the analytical proof, but this quantity, let us understand that what is preserved even after transformation. Suppose you have 4 collinear points, x1, x2, x3, x4. You also note their order of appearances in the point. 2 terminal points are x1 and x4. x2 and x3 are 2 intermediate points. So cross ratio is defined as, you can see, ratio of ratio. So this is x1, x2 divided by x2, x4, this part, and the other part is x1, x3 divided by x3, x4, and the ratio of these two. Now this is preserved. So if I have a transformation, for example, as I maintain the order is preserved. So suppose this x1 is transformed to y1, this x4 is transformed to y4. Similarly, this x2 is y2 and this x3 is y3. So this is the same order. You see y1, y2, y3 towards y4. This is the appearance of the intermediate point would be there. So in this case also, if I compute y1, y2, length of y1, y2 divided by y1, y2, y4, ratio of say y1, y3 and y3, y4. So this ratio and this ratio for the same straight line and the same set of points, these two ratios will be the same. So this is under projective transformation, they remains the same. So this is the kind of interesting feature. Now let us consider the affine group. So when you are considering affine group, in the affine group, as I mentioned, the last row would be in the form of 0, 0, 1. So that characterizes an affine transformation, and which means that all these 6 elements, now they become unique under this representation. When it is 0, 0, 1, all these 6 elements are unique. So since these are 6 elements and you need to determine, suppose I give you point correspondences for affine transformation. So as I said that suppose this is x and this is x prime. So I can write x prime equals HAX. But from there, I will get 2 equations, because the last equation, that from the affine representation, last equation would be always 1 equal to 1. So last equation is irrelevant. So I will get 2 equations, and in this way, since there are 6 unknowns, only 3 point correspondences would be fine to compute the affine transformation. So if I know that projective transformation is affine, I do not require minimum 4 point correspondences. 3 point correspondences are fine. Even as you understand that it becomes a homogeneous, non-homogeneous equation. So your estimation methodology, just you can apply least square error method, and you can get the estimated points, estimated matrix. Now, to understand that what kind of transformation takes place under affine transformation. So here what is done is that when I am considering a transformation, we actually introduce non-uniform scaling along some direction. So I mentioned this part during projective transformation also. In affine transformation, this is particularly true. And here, once again, see, along this direction, if I perform this, so what we would like to do, that first you rotate this object by the angle phi, and then you consider the respective non-uniform scaling, and then you perform the back rotation to bring it into that structure. After that, the whole transformation is rotated by theta, and also there are translation parameters. So with this, this D is a transformation diagonal matrix. It is lambda 1, lambda 2. These are the non-uniform scaling. So you are rotating by phi, angle phi. Then you perform non-uniform scaling. Then you again bring it back to its native state, and then you perform the coordinate rotation of the coordinate transformation theta. And before that, you also perform the translation. So this translation has to be performed. So there are two parameters for translation. There are two parameters for this kind of rotation, one for the coordinate axis, one for the rotation of for providing the non-uniform scaling along certain arbitrary direction, and two for the non-uniform scaling. So there are total 6 parameters. Like there are 6 independent parameters, and similarly there are 6 unknowns or 6 coefficients in the projective transformation matrix. So these two matched very directly. So these are degree of freedom is 6, and in the case of affine group, you can see that actually if I transform any ideal point, still it remains ideal. So say this is the thing. So this is an ideal point because the third dimension is 0. That scale dimension is 0. And if I multiply it, you apply the matrix algebra, which means you are multiplying A into this and then plus T into 0. So which is 0. So plus, here actually plus 0 is there. Then 0 into this, 0 transpose into x1, x2, which is 0, plus B into 0, which is equal to 0. So effectively, finally you will get this kind of resultant operation. Now since ideal point is transformed into another ideal point, it means that parallel lines, they still remain parallel in the Euclidean sense. They are not intersecting, but their point of intersection at the point at infinity in the projective sense, that gets transformed. That does not. So direction of parallelity changes. So this is one of the invariance property. So line at infinity still stays at that line at infinity. It remains the same, because all the intersecting points of parallel lines, they lie at that line at infinity, and still they are remaining ideal points. So line at infinity remains the same. So if I perform the transformation, say if I perform affine transformation in the projective sense with the line at infinity, so you know that I have to do that. I have to apply the transpose of inverse. Then still I will get it is in the projective sense. That means I can multiply with any k also here. So still I will get the same line at infinity. So that is the property of this kind of affine transformation. So these are the few things just to summarize that what are remains invariant. One is parallelism, then ratio of areas, ratio of lengths on parallel lines, for example midpoints, then linear combination of vectors or centroids, and the line at infinity. So these are few invariant things. Next we come to that this Euclidean group. Actually this is also called similarity group. Now in this Euclidean group, what I mentioned earlier, that these submatrices, they are orthogonal. Now when we are saying orthogonal, which means that now we can express this orthogonal matrix in this form, you can see this R is the respective rotation matrix. Here actually R is representing like a rotation matrix in the geometric transformation, which is orthonormal, and there is an uniform scaling. So under similarity group, rectangles still remain rectangle. So that is what is there. And then you also there is a translation parameter, but rectangle could be rotated. So you have a rectangle, then it could be transformed, it could be rotated, and it could be shrinked or expanded, but aspect ratio still remains the same. So there is only one scale, there is no two scales. So how many parameters you have? You have this rotation parameter, translation parameters, these are the coordinate transformation parameters, and then you have the scale parameter. So there are only 3 parameters. So in this case, if I want to estimate a similarity transformation or similarity matrix, then I require only, as you understand, 2 point correspondences, because from each point correspondence I will get 2 independent equations, and since there are 3 unknowns, I will get a set of overdetermined set of equations, and 2 points are sufficient to give me a similarity transformation. So as I mentioned, degree of freedom is 4, 2 translation, actually degree of freedom is 4, not 3, 2 translation and 1 rotation and 1 scale. So these are the 4 parameters, 4 transformation. One of the interesting fact here is that there are 2 fixed points of this transformation. Now what is a fixed point of a transformation? If I consider, say, a transformation of an element x, and when it becomes x prime, it's a transformation, as you can see with respect to this linear transformation. So when x and x prime both are same, then x is called fixed point, because it is transforming on the same point. So if I again apply h, it will be again the same point. So this is called fixed point of a transformation. Now there are certain transformations when you can do iteratively. That means from any point, if I go on doing these things, finally you will arrive at a point which will still give me the same point. Now that is also fixed point of a transformation. But by definition, fixed point is that point where actually you get back the same point. Now here there are 2 interesting points. You can see these points I and j I have shown, but the fact is that these points are not real coordinate of the real space. They are the coordinate in the complex coordinate space. So this is the complex number. This I is that root over minus 1, that imaginary unity. This minus 1 is minus root over minus 1. So you have a complex number representation. So far we have dealt with real numbers, we thought that, but even the complex numbers can be used in the vector representation. And if I apply transformation, I will get again a vector in the complex number representation. So if I apply this computation, say this is a similarity transformation matrix, this one, and this is this point I. So you can see that after multiplications, I get a scale factor which is a complex number, and I am getting the same vector. So in the projective sense, once again, that scale ambiguity, considering scale ambiguity, it is the same point. So that's why it is a fixed point. Once again, it's a concept in the projective space. So if I consider hard equality, it was not. But in the projective sense, it's a fixed point. The same thing happens for this one also. Same thing happens for this one also. So these 2 are the fixed point of similarity group. There are certain interesting properties of these 2 points which will be revealed later, which I will discuss later. Actually, these are called circular points. There is some reason for that. I will come to that thing later on. So these are the things, like what are the things which are invariant under similarity group? Ratios of lengths, angles, and the circular points I and j. So these are the invariants of the similarity group. Then come to the last speciality, which is oriented Euclidean group, and which we consider isometry because it preserves the distance between two points even in the transform space. So whatever the distance in the original space, say consider your original space and you have 2 points, and its distance, whatever distance you have, even after transformation, right? Even after transformation, it preserves the same distance. So it is a kind of like a rigid body transformation, but there is one difference is there. It can preserve orientation, then it is actually a rigid body, and it may be reflections. So it can be in the opposite direction. So then it is not like it's a rigid body, but it's a different kinds of transformation. So anyway, so they are actually the scale value. All the scale value should be 1, but the change of orientation, this epsilon, they make the epsilon could be 1 or minus 1. So either minus 1 or 1. So, and there you can show that it preserves the distance. It preserves the distance between 2 points. So if you have a rectangle, now it is transformed to a rectangle of same size, but its orientation may change. So what are the number of parameters in this case? The number of parameters, because this is constant, either plus 1 or minus 1, if I specify it, then theta, that rotation and translations, the coordinate transformation, this is only 3 parameters. So in this case also you require only 2 points to estimate. So 1 rotation and 2 translation. And what are the invariants? Now you can see the length is the invariant, angle is also the invariant. In fact, in the similarity transform also angle was the invariant, and then area remains the same. So earlier it was ratios of areas, but now area remains the same. So that's why it is called isometry. There is a term what is being used here. Another interesting fact, what we would like to discuss here, that if I consider any general projective transformation, I can always express it as a decomposition of series of projective, then affine and similarity transformations. And there are certain special structure for that. You can see for the projective transformation, I am only considering the transformations related to line at infinity. So this parameters B, that is only considered. So V is only, this is only scale. So only there are 2 parameters, right? Then you are applying the affine transformations. You see that this is affine because this last row is 0, 0, 1, and this K is also, it is upper triangular matrix, which means the structure, if I consider for this element, this is A11, say this is A12, this should be 0, and then this is A21. Then this one is a similarity transformation. So here is also the parameter S and R is there. So in the similarity transformation, you have the coordinate transformations related to translation, rotation, and also scaling. So these are the similarity, and then you can consider the affine transformation. You can also take the inverse of this transformation, and that would also give you another transformation. So if I take H inverse, for example, I will get HP inverse, then HA inverse and HS inverse. It is the reverse order. So as you understand, as I mentioned, all of them are groups. So this is still projective transformation, and it will remain in the same structure. This is still affine transformation in the group, and this is still similarity. So it can be also considered the other way. That means first you apply the similarity transformation, then you apply the affine, and then you take the projection, consideration of the projective transformations. So these cascaded forms are useful sometimes to understand the geometric transformations that takes place in a composite projective transformation. Those factors, it can gives you those factors. So there are different ways you can compute these factors. So one of the algorithms I have just expressed, because with this kind of decomposition, this A, if I apply the matrix multiplication, it could be expressed in this form. And as you can see that already in the projective transformation, these are defined. Already it is defined. So this B transpose from the transformation matrix itself is you can get, and also translation factor also from the transformation matrix you can get. So from there you can get this component, which is once again a 3 cross 3 matrix. That means this should be equal to A minus TB transpose. Now this is actually 2 cross 2. this A is a 2 cross 2, so 2 cross 2 matrix. Now this one, there is a scale associated S, and this R is an orthonormal matrix and this K is a upper triangular matrix. Now there is a QR decomposition algorithm where Q is an orthogonal matrix and R is an upper triangular matrix. So using QR decompositions, you can find out these factors, and by making, taking out S from the orthogonal matrix, you can make it an orthonormal operations. You can adjust them, you can make it orthonormal matrix. So, and S can be taken outside. So, by this, in this way, you can derive all the factors. So, an example, just to show you this example, you can see that this is the thing. This determinant of K is equal to 1. It has been, some constant has been also given just to put the limit on S. So, this is H, and this is one example that how this projective transformation can be explained in terms of series of projective transformation, where you can see this is that I, and this is that corresponding V transpose, and this is that K, and this is SR, and this is the translation. So, from there you can explain different kinds of parameter configuration. So, with this, let me conclude, let me stop here, and we will continue this discussion for the next lecture. Thank you very much for your patience and listening.